We kind of landed on kind of awkwardly in the middle of this example last time, so I'm going to go ahead and recap part A, which I completed, and then move on to part B. So let me remind you first, we're doing a static friction on an incline. We have that this object stays at rest. It's being acted upon by three forces. Gravity pulls it down, the normal force acts perpendicular to the surface, and as we learned, those two forces alone would cause an acceleration or slide down the incline, so frictional force holds it back. It's static friction if it stays at rest. And so the givens I'm going to give you are the mass of the object, the angle of the incline, and the coefficient of static friction, which is a measure of the roughness of the surface when the object is stationary on it. So the larger this value is, the rougher the surface is. And I've given you numerical values, even though I'm going to solve first symbolically because it's nicer to have the numbers when I kind of want to make certain points. So just to give you a recap, as usual, we split up the force of gravity into components. There's a part that goes directly into the surface, and that's offending the normal force, so those two are going to cancel. That's where the y direction comes in. The normal force just cancels off the mg cosine theta. That was true on a frictionless inclined plane as well, because even though you could slide down the incline on a frictionless incline, plane, you still can't move into it, right? You still can't crush the surface. So this is necessary for the structural integrity of the surface to be protected, whether or not you're sliding along it or not. Now over here, we had an mg sine theta, which was free to then be the net force on the object and cause it to accelerate. In fact, you did the frictionless inclined plane example on homework 4. But now, if it's possible for this to be canceled off by the static friction, that's what holds it in place. And so we worked out last time that, of course, the static frictional force has to hold back mg sine theta. And I pointed out, if you plug in the numbers, you get that mg sine theta is 34 newtons in this case. Hopefully I've done that correctly. 10 kilograms times 9.8 times sine of 20 degrees. Now that is far less than the maximum value of static friction, which we learned can be computed by taking the frictional coefficient and multiplying it by the normal force. In this case, we of course know that the normal force coming from over here is mg cos theta, so if I've done this correctly, putting in mu sub s mg cos theta gives you 74 newtons. That tells you that on this incline, the maximum frictional force could be 74 newtons, but it isn't actually 74. You only need it to be 34. So just like in our discussion from last time, in this circumstance, the frictional force could be anywhere from 0 up to 74 as needed before it gave out, but it's only 34 because only 34 newtons are needed. So mg sine theta is not pulling nearly as hard as it could be. So static friction is certainly not maxed out. So make sure you understand why, even though mu sub s times n comes out to be 74, the actual frictional force is actually 34. And of course, the reason why static friction force isn't maxed out yet is because we're at a fairly moderate angle. We can actually tilt this much further before friction gives out, and so that's where I want to kind of where we ended up last time. We didn't get a chance to crack part B, where part B, of course, is going to calculate, well, what is the maximum angle? So 20 degrees is not it. We can tilt this up steeper. So let's take a little bit of a look what happens when theta increases. So it might be helpful to draw what it looks like as a much steeper incline. So maybe something like that. Theta is certainly larger. And if we take the force of gravity, might look something like this. I want to remind you about the kind of what happens on an incline if we again break up the force into two components, one that's directly into the incline and one that's directly along the incline. Of course, we've drawn those up here, mg sine theta and mg cos theta. What we see is that we're kind of proportioning gravity in a different way. So of course the total force of gravity is the same, but how much of it goes into this component versus this component is going to change. So hopefully you can see that the mg sine theta component is increasing. So that's this one. It's the part that pulls parallel, right? In fact, it's the force that's trying to move it. It's the force that's trying to get this sliding action going. So this is trying to move it, trying to slide it, I guess I can put it. I'm sorry that I know the text is really small, but it says trying to slide. And simultaneously, the normal force, which is the contact force, is going to decrease because the force of gravity component that's pushing into the surface and creating that contact is going to decrease. So mg cosine theta is going to decrease. And this is the force that's creating the contact. Sorry, again, that's a little small. That says creating contact or creates contact. Let me separate that. So you can see what's happening here is that we're going to come to a head at some point because if the force that's trying to slide it is getting bigger and the force that is kind of helping hold it in place is decreasing, at some point you're going to have that it doesn't work anymore. If you want to see a visual representation, we have that this component is getting bigger, and of course if you put more of gravity into one component, then you're going to take it away from this one. So this one's going to decrease. So this one's going to get larger, increase. This one's going to get smaller, decrease. And of course if this decreases, then this decreases because they have to cancel. And remember that the maximum frictional force depends on the normal force, so this is going to decrease. So what you have is that the force trying to move it is getting bigger, and the force that's trying to help it stay in place is getting weaker. So at some point, this gets big enough and this gets small enough that we have problems. So let's work it out. When theta goes to theta max, by definition that means that the force of static friction is now not going to hang out somewhere below the as needed, easily able to cancel it off, the force is trying to move it. We're going to have to go to the maximum value. So the force of static friction becomes its maximum value, and of course we know that that's calculated by this. So rather than this being a less than sign, now it's going to be an equal sign. So mg sine of theta, which is the force trying to move it, if we're at the maximum angle, by definition, that's going to have to be equal to the maximum frictional force. So this basically is a statement that the force trying to move it is now so large that static friction has to be its maximum value to keep up. So this is an expression which can actually be solved. Okay, so this is trying to move it, and this is holding it in place, and because we've invoked the maximum value, it's barely able to hold that in place. Okay. Now we can solve here. This is an expression where we can just cancel off the mg's. We can group sine and cosine together into tangent. And we find that the tangent of theta max is mu sub s. And if we apply inverse tangent to both sides, we can find that's our expression. Now, your intuition about inverse tan, the inverse tan function may not be very good, but I'm just going to tell you that the fact that there's an inverse tan here doesn't really affect things very much. In fact, it still turns out that if you increase mu sub s on this side, theta max increases on this side. And this basically hopefully gels with your intuition about friction. If the surface is rougher, the maximum angle at which you can stay in place on it is larger. So if you were, say, trying to climb up a hill made of ice or Teflon, it's a lot harder than if it were made out of something rougher, because when something's rougher, you can stay on it to a larger maximum angle. So let me go ahead and give you the answer. Inverse tan of mu sub s, if it's 0.8, make sure your calculator's in degree mode, and I believe that should come out to be about 38.7 degrees. So 38.7 degrees is the biggest tilt at which this object could stay at rest. That's certainly bigger than 20. We found that staying at rest at 20 degrees was no problem. In fact, at 20 degrees, the force trying to pull it and get it moving is 34 newtons, whereas the maximum force you would have to hold it in place is 74 newtons, which is, of course, substantially larger, so you don't even need all of it. You just need the 34. Now, if you go ahead and plug if you plug this angle back in, hopefully I'll convince you that everything we said should happen does. If you take mg sine of 38.7 degrees, this number is now 61 newtons. So remember we said that should increase, right? The force trying to slide it should increase. We're on a steeper incline, so the amount of the force of gravity that's pulling parallel to the surface is larger. So this did indeed increase. Now we have 61 newtons trying to get it starting to get a motion. Now at the same time, we said that the contact force decreases. So if you actually calculate the maximum frictional force, this quantity here, you'll get that is now 61 newtons. So it has decreased. Our frictional capability has decreased. So notice these numbers are the same. So we have found that 38.7 degrees is the angle in which the force trying to move it, 61 newtons, the frictional value has to be maxed out at that angle to hold it at rest. So that is the end of the line. If for larger angles, what's going to happen is that mg sine theta is even larger, and it's going to exceed the most that friction can hold back, and so it will have to slide. So that's what happens for larger theta. Theta is bigger than theta max. In this case, bigger than 38.7 degrees, something will slide. So if you place it on the incline, it cannot stay at rest. Static friction is not strong enough to hold it in place. The force trying to move it, mg sine theta, is going to be larger than the maximum force available to hold it back. Interestingly, I should point out that this final expression, this is again something we notice if we solve symbolically, it doesn't depend on mass. So that says that if you and your friend are trying to climb the same hill, you don't have to worry about who can stay on there at rest, even if your friend weighs twice as much as you do, because it only depends on the roughness. So the roughness is the only thing that is going to affect it. If your friend's shoes are, for instance, smoother than yours, then that's a problem. But the fact that they weigh more than you do, have more mass than you do, is not a problem. A good strategy that I always advocate, if there's something surprising in that to you that it's missing in the answer, well, it canceled somewhere. So going back and seeing where it canceled might be informative of what happened. Now the mass is here before we cancel across both sides. Now if you have more mass, then the force trying to move you down slope is bigger, right? Mg sine theta is bigger if m is bigger. So that you might think, okay, well, that means that if you have more mass, then the force trying to move you is larger. Shouldn't that mean that you slide easier? Well, where did that mass cancel? It cancels with this mass. Now this is the force helping to hold you in place, right? This force is the other component of gravity, and it creates more contact. So that's why it ends up canceling, because the force of gravity, yes, the force of gravity is larger on a larger person. If m is larger, then f is larger. But we see that the force of gravity is automatically put into two pieces. one piece which tries to move you, and the other piece which helps hold you in place in that it increases the normal force. So it ends up coming out in the wash, the mass doesn't matter. Again, that's simply because if your mass is larger, the force trying to move you is larger, but so is the force helping to hold you in place. That's the end of that example, and what we're going to do from here, that really takes care of the heavy computation on homework 5. So now it's just a little bit of cleanup on certain topics. And I've saved the easiest stuff for last here, simply because I wanted to get the hard stuff on the homework discussed earlier. So now I want to compare static versus kinetic friction, which is kind of an odd comparison because you should never be using both of those at the same time. That would be double counting friction. Basically, these are both different styles of friction, and we break it off into this two-pronged attack simply because it's complicated enough that it's helpful to pick one or the other. You should never use both simultaneously. For this, I want to appeal to some kind of anecdotal evidence that you may have. If you ever try to move something heavy, you may notice that sometimes you push, and then when it actually gets moving, it almost gets away from you. Oh wow, that made some big scuffs on the paper. Well, hopefully I can deal with that. And so the reason why that is because the force that is necessary, I should say the minimum force necessary to move an object from rest is bigger than the minimum force to keep it in motion. And so, of course, the way that you adjust for that, if say you're moving like a heavy piece of furniture, is that you're an intelligent person who can exert a force that varies with time. So you push harder at first, and then you back off. And so let's talk about what these forces are. If you have an object that is at rest, the force you're trying to overcome is static friction. So if you're pushing, you're trying to overcome the static frictional force. So the minimum force necessary to move an object from rest, that's going to have to be ever so slightly more than mu sub s times n. That's your maximum frictional force you have to deal with when something is stationary. So if, for instance, if this value came out to be 5 newtons or something, you'd have to push 5.00001 newtons, right? Just barely more. If you have an object that's already in motion, then the minimum force you need to push to keep it going is just to counter kinetic friction. Of course, if you pushed harder, then you would make it go faster. If you pushed less hard than friction, then friction would eventually would win and eventually bring you to a stop. So you just basically need to have these two forces cancel, and then of course Newton's first law tells us that this will keep the motion it already has. So the minimum force you need to exert to keep something in motion is mu k times n. That's of course the kinetic friction force. So if this is greater than this, then we have this, and if we cancel off the normal forces, then we come to the conclusion that the static and kinetic frictional coefficients have this relationship. So you may have been wondering, why do we rate the roughness twice, right? Why do we have to talk about the roughness when you're sliding and the roughness when you're not sliding? Well, the reason why we have to rate the roughness twice is because it turns out that when the object and surface are stationary, they get a little bit more acquainted, and a few more kind of temporary chemical bonds form, so that the roughness is kind of a different thing than if you're sliding across. So if you're sliding across You just don't, the object just never has a chance to get that much acquainted with the surface, and so when we have to rate the roughness, it's in a certain sense a little more smooth. Of course, it's not that it's any smoother or rougher, but these are kind of our empirical ways to relate the frictional force to the normal force, and so that's why the values are slightly different. So this is in the general case, you'll find that the static frictional force at most is going to be usually larger than the friction you have to contend with once you're sliding. This is something we just find experimentally, and so it's reflected in these measured coefficients. And so what I want to look at now is what are the possibilities if you have a constant push that acts on an object at rest. So we're taking a look at the possibilities here. And so here they are. The first possibility is that the pushing force is not enough. It's less than or equal to the static frictional force max. If that's the case, the object stays at rest. Okay, so you're not pushing hard enough to get it moving. And by the way, when I say pushing force, you don't have to strictly have that be a pushing force. In my last example, of course, the thing that played the role of getting the object going was not literally a push, but mg sine theta. So what I mean here is anything that could try to get the object to move. If that can't overcome static friction, then you won't move it, it'll stay at rest. The other possibility is that the pushing force is greater than that. And now, of course, the object will not stay at rest because you've pushed hard enough to get into motion. So let's take a look at what its fate would be from there. Well, if you push hard enough to overcome that, we've just learned that you will definitely be bigger than the kinetic frictional force, because the kinetic frictional force you'll have to contend with once you are moving is even smaller. So the pushing force will definitely be bigger than the kinetic frictional force. So the forward force is bigger than the backward force. So not only will you get it moving from rest, you will continue to accelerate it indefinitely. So those are the only possibilities that could happen if you're applying a constant force. You could either not move it at all, or you will get it going from rest and it'll continue to go faster and faster indefinitely because the forward force is bigger than the backward force. Now obviously this is not a desirable outcome if you're, say, moving heavy furniture, because first of all, you don't want to have the furniture stay at rest, but you also don't want it to go faster and faster and faster. And so of course you're an intelligent human being and you don't have to apply constant force. You can apply a bigger force at first to overcome static friction, and then you can back it off and balance it out with pushing force later. So you can push harder at first to overcome static friction, and then you can back it off and decrease that pushing force when you just want to cancel off the smaller kinetic friction. And so what would you do in a problem like this? Well, the net force forward would be the pushing force minus the kinetic friction force, and that would be ma. You may wonder, where do you include the static frictional force, because you certainly had to contend with that to move it. Well, you're correct that maybe the first couple micrometers or something, the frictional force was a little stronger, but we throw it away because if you're going to slide 5 meters or something like that, most of the journey is going to be with kinetic friction. So again, you're only ever going to use one form of friction at a time. You should never have the static and kinetic appearing simultaneously. So in this case, because we do move, we just employ the kinetic. So I think there's a couple parts in your lab and in your homework where that's asked about. But again, in a general problem, you're going to use one type of friction or the other, but not both. Okay, so the final order of business that we have is to talk about Newton's third law. So let's do that. Newton's third law, and let me start with a recap of Newton's laws so that we can kind of see where the third law fits in. The first law talks about an object when it's left alone. Okay, so before we ever let an object be poked and prodded, we want to establish what it does. So, of course, learned that if you leave it alone, that means the net force is 0. And we learned that the object just keeps doing what it's already doing. So that's basically the first law. We learned about this idea of inertia, that an object will continue to do what it's already doing, whether that be staying at rest or staying at some very, very large velocity. It's going to stay there if you leave it alone. The second law says, what if the object is acted on by the environment? So then we of course said if you do have a net force on the object from its environment, it will accelerate. So it will be forced to do something different, it'll accelerate, and the amount of acceleration it experiences, of course, is related to the inherent stubbornness of that object to change, and that's measured by mass. The third law says that an object cannot be acted upon by the environment without the environment being acted upon by the object. And so basically, it really tells us that the distinction between object and environment is really one of just what you're interested in. The universe is made out of a bunch of objects. The one that you're interested in is called the object, and then everything else is called the environment. But one person's object may be another person's environment. Let's take a look at what this law says. I guess I should mention, you may have heard of it as the action-reaction law. So for every action there's an equal and opposite reaction. So I don't like that phrasing of it because it's imprecise. Let me give you a slightly more accurate version. Here's what the third law says. If object A exerts a force on object B, then, okay, and let me stop there and point out that it's not the job of this law to say if this is true, okay? That you have to figure out by other means. So does object A exert a force on object B? Well, you would have to figure that out separately. This law simply says, if that is true, if you know that's true, then there's something that follows. It says, object B exerts a force on object A. So it basically says that you can't exert a force without feeling a force back on yourself, okay? So an example would be, for instance, if I have an object A and an object B, if A exerts a force on B, then B will exert a force back on A. And by the way, I should mention that not only is that true, but it puts very specific conditions on what that force is like. It's equal in size and opposite in direction. So if I draw this so and so many newtons to the right, then the force back on A is so and so many, it's the exact same amount of newtons to the left. They're equal and opposite. I guess I should mention there's a way to label this. If you put the first subscript, that's usually what the force is on. So this would be the force on B. And then if you put a second subscript, that's where it comes from. So this is the force on B from A. So again, the notation is force, what it acts on, and the second letter, if you bother to include it, is where it comes from. So this is the force on B from A, and then this, of course, would be the force on A from B. And so one of the ways you could write Newton's third law in kind of an equation form, if you wanted to, was FAB equals negative FBA. So that's basically saying they're equal in size. The extra minus sign is, of course, they're opposite in direction. They're not equal, they're equal and opposite. So here would be an example. I guess I'll use this. I guess this will be my object B, and I'll be object A. And so I can decide to push this object to the right, and I will be pushed back to the left. So I know that's hard to imagine, but I'm in a rolly chair, so if I push something, I get pushed backward. You can try it yourself with something heavier, and if you push it away, it'll push you away. This is by no means, it has to be in this direction. You could also do it the other way. Instead of being a repulsive force, you could have that maybe the force on B from A is such that B gets pulled toward A. Well, the law says that A has to be then pulled towards B. So it's an attractive force now. So you can imagine if you pull something toward you, you'll be pulled towards it. So again, I'm sorry that the demonstration's a lot easier in the classroom, but kind of had a glitch today. So these forces always appear in pairs. You have either neither of them are there or they're both there. So they're kind of inseparable. They're kind of like twins. You have them both. They get a name. This is called an action-reaction pair. Now which one's the action and which one's the reaction, it doesn't really matter. They always appear together, so basically there's no reason to assign one of them as being called the action versus one being called the reaction. The statement of the third law that you often hear is, for every action there is an equal and opposite reaction. The reason I don't like that is because, first of all, what's the action? Well, action is a force. What's a reaction? It's another force. Which one is which? It doesn't matter. The other thing I don't like about it is that it doesn't say what is on what. So for every action there is an equal and opposite reaction. Well, what are these things acting on? So there's kind of rampant abuse of that idea. For instance, your friend wants you to go outside and you're sitting on the couch and you say, well, I'm sorry I can't get off this couch because if I try to act and get off the couch, there will be an equal and opposite reaction that keeps me on the couch. That doesn't make any sense. Obviously you can get off the couch. And the reason why that is a fallacy is that you're attributing both forces onto the same thing. So the law does not read if object A exerts a force on object A, then A exerts an equal and opposite force back on A. That doesn't make sense. If that were the case, then nothing could ever feel a net force. So what actually happens here is that each object gets one force, and each object is perfectly free to accelerate in response. So note that a force, I guess I'll say the action and the reaction act on different objects, okay? The third law is an interaction law, so it's saying how two objects affect each other. So they both feel a force. Now, I am certainly not claiming that they will move the same. They may have very different accelerations, but that's simply because of their mass. So just because two things feel the same force, one may be more massive and feel less acceleration in response, and one may be smaller mass and have a much larger acceleration. Okay, so I'm not saying that the accelerations are equal and opposite. The forces are. Make sure you remember that. The forces are equal and opposite, but the accelerations that will result may not be because they're different masses. Okay, so let me actually show you an extreme version of that. I'm going to have a baseball and the entire Earth. I'll call this mass little m, I'll call this mass of the Earth. And so we know, of course, that the baseball falls down because there's a force of gravity. And now we understand that if the baseball gets pulled down by the Earth will get pulled up by the baseball. The forces are exactly the same size, and in fact, let me just write that here. Let me leave off the vector hats. That just indicates size, so I don't have that pesky minus sign I have to throw in there. So the force of gravity on the baseball, it has a mass m, and the acceleration that's caused is, of course, the very well-known 9.8 meters per second squared. And the force on the Earth, well, the Earth is just way more massive. And so the acceleration of the Earth is very tiny in comparison. It's tiny. So it's not that the forces aren't equal, it's just that because there's such a drastically big difference in the masses, the accelerations are nowhere near each other. While this may be a sizable 9.8 meters per second squared, this, in fact, is so tiny that it's going to be extremely small number. But notice, it's not zero. Because if this were truly zero, then this equation would not hold. So it's actually technically true to say that it's not that the ball falls down and hits the Earth, it's that the Earth and ball actually fall together. Now, it just so happens that the accelerations are such that this does almost all of the actual motion, and the Earth accelerates up so little, it actually falls up about the billionth of width of an atom. It's extremely tiny, but not zero, because if the Earth is going to exert a force, it feels the force back on itself. So it's technically correct to say that they fall together. That we say that the ball falls down is just recognizing that the ball actually does most of the accelerating. It does most of the motion. Not all of it, but almost all of it. So with that in mind, I'd like to do the, this is very similar to one of the examples on the homework. This is going to be me holding a brick in my hand. Okay, so something like this. Okay, so I'm just going to hold it in place like that in my hand. I'm not going to move it at all. And let me draw it. Like so. Now I drew it like that not because the brick is levitating above my hand or something like that. It's just I want to just create a little space in there because my labeling is going to get unclear. So imagine I'm just kind of breaking out everything so I can look at it. So let's go through here and talk about the forces that act on the brick. We have the force of gravity, which pulls down on it, and we have the support force from the hand, which we usually call normal force. So let's talk through this. Are these forces opposite? Yes. So are they opposite in direction? Yes. Are they equal in size? Yes. Are they an action-reaction pair? Well, this is the tricky one. No, they are not. Okay? We got tricked into thinking that they were because they're equal and opposite, but that's not enough in this case, as we will see, because any two forces can happen to be equal and opposite, but action-reaction pairs are always equal and opposite. Now, what's my first clue that they're not an action-reaction pair? Remember that action-reaction act on different objects. These both act on the brick. So The law, again, does not go if A exerts a force on A exerts an equal and opposite force back on A. These are not an action-reaction pair. So we need to figure out, if they're not a pair with each other, where's their partner? The easiest way to do that is to write out what the force is on. Force on the brick from the earth. So that tells us what's the action-reaction pair. There's a force upward on the earth. So this is the force on the earth from the brick. I just reversed the two nouns in the sentence. There's my action-reaction. By the way, it's the same action-reaction pair that I had here. So what you notice is that these two always have to appear together. There was no normal force in this case, of course, because the ball was falling. So I had the force of gravity on this object, but there was no normal force. Here, I happen to have one because I'm holding it instead of letting it fall down. So these two are a pair. Let's find the pair for the normal force. Where is its partner? So that is the force on the brick from, well, now it of course comes from the hand. So what does that mean? That means that there is an equal and opposite force on the hand. So I'm going to mark that. So if the hand pushes up on the brick pushes down on the hand. So I'll label that partner. It's force on the hand from the brick. That's an action-reaction pair. Those are always equal and opposite. So the normal forces, that's a pair. That's an interaction between the brick and the hand. The force of gravity, that's a pair. That's an interaction between the brick and the earth. But the original two were not a pair. I'll go ahead and circle that. These two happen to be equal and opposite, but since they weren't partners, they don't have to be. In fact, in the last example that I talked about over here, the force of gravity was something and the normal force wasn't even there. So these two definitely don't have to be equal and opposite. In fact, the normal force need not even be there. So what's my evidence for this, that these don't have to be equal and opposite? Well, I can decide that I'm not going to hold the brick in place. I'm going to accelerate it upward. So what do I do there? I'm going to make this force bigger. So then, if I look at the two forces, F net equals ma, now of course my force here, the normal force and mg are no longer going to cancel. That's where the acceleration arises from, is the fact that the forces on the brick are no longer in balance. But if I make the normal force bigger, its partner has to get bigger. These two, the normal forces, are always equal and opposite, so if you make one bigger, the other one's bigger. So they always track together. They're always equal and opposite. If you turn one off, the other one turns off. You can do that by pulling your hand away. What you're really doing when you're working with Newton's second law, you're gathering up halves of action-reaction pairs. So what you're doing here is you're gathering up things that act on the object of interest. So all the different ways that it interacts with the outside environment, right? So this brick interacts with the hand, that's a part of the outside environment. This brick interacts with the earth, which is you've classified as the environment. So this is your environment. And this is your object, is your brick. So that's basically an artificial distinction you've made because you're interested in how the brick behaves. You're interested in finding out how it accelerates because of the outside world. You're gathering the halves of these action-reaction pairs that are acting on the object of interest. That's step one of your forced problem-solving strategy. But you are you're not going to calculate anything about the hand, so you don't need that. You're not going to calculate anything about the earth, so you don't need that. So you're tossing away the other part of the pair, and you're just keeping the part of the pair that's acting on the object of interest. Okay, so that's essentially what you're doing when you're working with Newton's third law. Okay, so that'll do it for this lecture, and that is also the end of homework number 5 and exam number 1 material. So you can put a line in your notes. You don't have to study anything after this for exam number 1, although next time I will continue with new material for homework 6.